Okay, so 4.17. So they want you to group the configurations and pairs that represent elements with similar properties. So when they're talking about similar properties for elements, there are a couple factors that we talked about when you're looking at the periodic table that help you to judge some of the properties for the elements. There's a variety of properties. We talked about the size or atomic radius. We talked about ionization energy. We talked about electron affinity. Moving forward, there are going to be other properties we talk about as well. And we said generally as we go from left to right, each element, the next element to the right as we move across the periodic table has more protons and more electrons than the previous element. But as long as we don't add those additional electrons to another energy level, then they don't really create that much more shielding, and by adding another proton it causes the electrons to get attracted in, and so that makes the atom smaller. It makes it have a higher ionization energy because it requires more energy to knock those electrons out when they're pulled tighter by the additional protons in the nucleus. And it makes a higher electron affinity because as we go from left to right, adding more protons creates a situation where it's more likely to attract an outside electron into the atom altogether. Except when we get to the end, because once we hit a noble gas, the noble gases have a very stable arrangement of electrons, and that arrangement of electrons is not likely to add a whole new electron in, because that new electron would have to go into a whole new level, and it would break up the situation where we have a stable arrangement of electrons. So even as we go from left to right, we see there are differences in the properties. We also see differences in the properties as we go from the top to the bottom. So this question is referring to elements with similar properties, and based on what we talked about, there shouldn't be any two elements that have the exact same property. So the word similar there is a bit subjective. You have to kind of read into what they're asking. It's not the best wording for a question, but what they're getting at is, if I look at a column here, what these elements in this column have in common is the same number of valence electrons. And we said, yeah, as I go from the top to the bottom, the size will increase. As I go from the top to the bottom, I'm adding more and more layers of electrons, and those outer electrons experience more shielding from the inside electrons, so they're not held as tightly. It's easier to knock them out. They have lower ionization energies. It's not as easy to bring a new electron in, because if it comes in, it experiences shielding from the core electrons, and so it has a low electron affinity. But because they're all in the same column and they all have the same number of valence electrons, that does give them some similar properties. And so probably there's more difference between elements on the left-hand side versus elements on the right-hand side than there is between elements on the top versus elements on the bottom. So if we look, for example, at the halogen, you see all the halogens have something in common. They're all nonmetals. They're all one away from a noble gas configuration. They can all make the same number of electrons as a noble gas if they pick up an electron, so they all have relatively high electron affinities. They're not all exactly the same, but they do have some similar properties as a result of that. On the other end of the extreme, if we look at the group 1A metals, excluding hydrogen, talked about that last time. Just looking at the metals here, they also have some similar properties. They all have low ionization energies and low electron affinities because, well, for the ionization energies, it's easy to knock one of their electrons out, excluding hydrogen, because it doesn't work for hydrogen. But for the other ones, if I knock an electron out, I get the same number of electrons as a noble gas. So if we're looking for elements with similar properties, usually we're looking for elements that are in the same column. So if I have the electron configurations, and I have those given, so the first one is 1s2, 2s2, 2p5. That element, assuming that these are all neutral, has a full 1s, a full 2s, and then 5 electrons in the 2p. So that element we're talking about is fluorine. Right? It's one away from a noble gas. It has 5 out of 6 position filled in its p subshell. So another element that might have a similar property, since fluorine's properties are mainly determined by the fact that it's one away from a noble gas, it has very little shielding compared to the number of protons it has, so it attracts electrons very well compared to other elements. That's fluorine's MO. That's what it does. If I have it involved in a molecule or if I have it involved in an ionic compound, its main thing is it's going to be attracting electrons. So other elements that attract electrons, not quite as well because they have more shielding, but also better than most of the other elements on the periodic table, is chlorine, bromine, iodine, because they're also one away from a noble gas configuration. So fluorine is in the 5th column of the p block, and chlorine and bromine also are. They should also have a p subshell with 5 electrons. So if I look through there and I'm looking for the same thing, I see D matches that. D has a 1s2, 2s2, 2p6, 3s2, 3p5. So again, that p subshell with 5 valence electrons in it is the key. And so G is representing element chlorine. So they have similar properties. So I would do that with the other ones as well. So if I see anything where the outer energy level has like the same number of electrons and the same type of subshell, they should have similar properties. So I can match up B and E. Because B has a 1s2, 2s1, so it has 1 electron in an s subshell. And when I look at E, it has 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this, in this situation, B is lithium and E is potassium. And they have similar properties because they have they have a very similar electron configuration. For their outer electrons, right, the inner core electrons usually held pretty tightly. We're not going to be usually removing those or adding to that area. We're talking about the valence electrons. That's what determines what the element's likely to do. What are the properties of the element? What kind of changes is it likely to undergo? That's mostly going to be determined by the valence electrons and what types of subshells and how many are in those subshells. So for 2 elements that have 1 electron in their valence subshell and it's an s subshell, they're going to be most likely to give that electron away so that the remaining number of electrons will be equal to the number of electrons as a noble gas. And then we can also compare C and F. Oops. Because they are both noble gases. C is 1s2, 2s2, 2p6. That's 10 electrons. That's neon. And I know the noble gases are in the 6th column of the p block. So anytime I see the outer subshell is something p6, 2p6, 3p6, 4p6, that's a p6, that's a noble gas configuration. And so that C and F are going to have a lot of similar properties because they have configurations that have a similar energy for their outer electrons. How many valence electrons? Okay, I actually didn't say that right. It's not that these 2 noble gases have a similar energy for the outer electrons. It's they have a similar configuration, similar arrangement. Their outer electrons are filling up a p subshell. How many valence electrons do the noble gases have? 8. Good. So the valence electrons are all of the electrons in the outermost principal energy level. So if that's level 4, that includes all of the electrons in n equals 4. That's the 6 in the 4p and the 2 that are in the 4s. That's 8. And I have the same thing here. 8 valence electrons for part C. That looks like a carbon and a fluorine. It's not. It's part C and F of the question. So this was neon. And the 4th one is krypton. Any questions about that?